Okay, welcome back everyone. In section 3.5 we've been discussing, let's say, big classes of projection methods, starting with the collocation method and then going on to Galyokhin's method. And in the end we made a comparison which showed that in the end Galyokhin's method is nothing but the finite section method on a Hilbert space. So we can happily continue to study the finite section method and thereby also study Galyokhin methods. Okay, but now it's time for a little insert on operator theory. And let me start with an operator A between two Hilbert spaces x and y. And let's discuss how we could check invertibility of that operator A. Of course, by definition, A is invertible if and only if it's injective and surjective. And we know how to check injectivity. You just have to make sure the kernel of A only consists of the null vector. So if the result of AX is 0, then the input must have been 0. However, checking surjectivity is not quite so handy. You would have to check whether the set of all outputs is all of y, but that's not so easy. Instead, let's recall first year linear algebra, when matrices were still finite, life was still easy, and we made the following observation. Injectivity of your operator means the columns of your matrix are linearly independent, or you could say after elimination every column has a pivot. Now surjectivity is exactly the same statement but for rows instead of columns. And then of course you could say, well, if it's so easy to check injectivity, why not look at A star instead of A? Because the rows of A become the columns of A star up to complex conjugates, and we could check linear independence of these rows by just checking linear independence of those columns. So that would just be injectivity here. And this connection sounds like it makes a lot of sense, and it's indeed true in finite dimension. But let's put a little question mark here and try to find out whether or not it's true in infinite dimensions. Okay, so this here is about the image of A, and that here is about the kernel of A star. How are these two spaces connected one to another? So let's start with the kernel of A star here. A star is going the other way around. It's going from y into x. So a little y is in the kernel of A star, if and only if A star turns it into 0. Now, because the output of A star is in x, that must be the 0 element of x. And the 0 vector of x is the only vector that is orthogonal to all other vectors in x. So now we are using that we have scalar products. So all elements of x are orthogonal to my vector A star y that claims to be the null vector. But now, of course, at some point the job description of the adjoint operator has to come in, so it jumps to the other side of the comma, where it's getting another star, but A star star is just A. And now if you read this out, it's saying that your vector y is orthogonal to every output AX of your operator A. You're trying all inputs, and no matter what you try, all outputs are orthogonal to your vector y. So you could as well say that y is orthogonal to the image of the operator A. Or you could use this shorthand for orthogonal subspaces, where this here is just the space of all vectors that are orthogonal to the set in this case also a space, in brackets. So we just derived this chain of equivalences where y is in a first set if and only if y is in that second set, but that must mean the first set equals the second set. And if you did singular value decomposition in your linear algebra course, then you might have seen this equality before. Okay, so is that helping to resolve our little mystery here? I guess so, because injectivity of A star means that the kernel of A star is just the null element. But now that is also the orthogonal complement of the image of A. And this looks kind of promising because it's saying that the image of A is so large that its orthogonal subspace is just the trivial subspace consisting of the null vector only. Okay, so can we conclude from here that image of A is the whole space and therefore A is surjective, which would eliminate this question mark? And unfortunately we cannot, at least not if the setting is infinite dimensional, and let me show you why. Okay, this is a space, that is a space. So equality still holds when we apply the operation of passing to the orthogonal subspace to both sides, and this is in fact an equivalence relation. And now, because this here is the null element in Y, we get on the left hand side the space Y, but on the right hand side the orthogonal complement of the orthogonal complement of a subspace is not that subspace, it's the closure of that subspace. And it could indeed happen that the closure of image A is the whole space Y, but the image of A itself is not. So it's not closed because it doesn't coincide with its closure. And I will show you an example in a second. But let's try to get this straight up here now. So we cannot remove the question mark, but we can kind of fix the problem. So our A is surjective, well, by definition, if and only if its image is the whole space Y. But this is almost what we have here. So let me copy this in here, but just as injectivity of A star, because that's what it is. Okay, and now we have that Y equals the image of A, if and only if Y is the closure of the image of A, and, well, closure of image A is image A, right? Well, because then you can put image A here, and then you indeed arrive here. So surjectivity of A means injectivity of A star and a little extra condition. Okay, so let's now fix this line here. So we can remove the question mark, and we have to put our extra condition here. Okay, so now we have it. So the invertibility of A is equivalent to the injectivity of A and injectivity of A star, and unfortunately the story is not over yet. You also need the image of A to be closed. These three conditions are equivalent to invertibility of A. Let's try to frame that very important statement. Okay, and here's my long announced example showing that we cannot neglect the green condition. We take the operator A that is acting via multiplication by this diagonal matrix. The diagonal entries are just 1 over n, where n is running through the integers. and let this act on L2. And I'm writing 2 here because we want Hilbert spaces. And this operator is just multiplying the first component of your sequence by 1, the second by a half, the third by a third, and so on. And it's easy to check that the output is 0 if and only if the input was 0. So this operator is injective. But on the other hand, A equals A star. It's just a diagonal matrix with real entries. So the transpose complex conjugate is still A, which of course implies that A star is injective. And that means we have both of our blue conditions here in force. So A is injective and A star is injective. And if we forget about the green condition, we would now say yes, A is invertible. But it's not. Why is it not invertible? Well, what would the inverse be? The inverse would have to be the diagonal matrix that has the natural numbers 1, 2, 3, and so on the main diagonal, and you can already see that this is not a bounded operator, right? So the diagonal is growing and growing. We know that the norm of a diagonal matrix is equal to the supremum of the diagonal entry, so that would not be a bounded operator. That gives us a somehow uneasy feeling about this, but in fact we can check directly that A is not surjective. And to do so, let's look at the element 1, a half, a third, and so on over here, which is clearly in L2 because you can add up the squares of these entries and get something finite. But what would the original input for that output be? Well, it would have to be the vector that is 1, 1, 1, 1, 1, because that's the only vector that after multiplication by this diagonal matrix gives you that output here. But this input is clearly not in L2. You cannot square the entries, sum up, and get something finite. Clearly not. Well, this means that this is not an output of this operator. It's not in the image. And so the image is strictly smaller than y. Okay, I think now we all see that A is not surjective. So injectivity of A star doesn't seem to guarantee surjectivity of A. And hence injectivity of A and A star together don't seem to guarantee invertibility of A. Okay, so in this example we have injectivity of A star, so we have that the closure of the image is all of y, but the image itself is not all of y, so it's not equivalent, it's not equal to its closure. Okay, so in infinite dimensional spaces you have to be careful. In finite dimensional spaces, every subspace is closed. So the green condition can be neglected when you're finite dimensional, but not when you're infinite dimensional, like we just saw now. Let's label our statement here with lemma 7 because it's very important and I'm sure we will have to come back to that. And for the following, let me label these conditions here. So the first blue condition is 1. And these here are 2 and 3. Okay, so 2 and 3 together give you surjectivity of A. Now my next point is to see that 1 and 2 in fact also belong together, because these two together give you something that we've seen before. And this will be our next lemma. Must be lemma 8 then. And it says that our two conditions, 1 and 2, if you take them together, are equivalent to the following. There exists a positive constant, let's call it little c, such that the output of your operator has norm greater than or equal to constant little c times norm of x. And that is true for all inputs x. And this statement looks a lot like boundedness of your operator, but it's not, because the inequality sign is the other way around. So what does it mean? So just like for boundedness, suppose for simplicity that your input has length 1. And now this time you can say that the output after applying your operator has length at least little c. So when we discuss bounded linear operators, we kind of discussed that the image of the unit ball under an operator is some kind of ellipse. And the ellipse is again centered at the origin. And we know that the maximal radius, if you want to call it radius, of that ellipse is the norm of A. But now this inequality is telling us that our output has length at least little c. So now little c must be the minimal radius of our ellipse. When we will talk about singular value decomposition, we will call that one smallest singular value of your operator and that one the largest singular value of your operator, just as a little preview. But maybe you even remember that one from your linear algebra course. Okay, and it seems kind of clear that such a minimal radius little c should exist, but on the other hand it has to be positive. So, I mean, in the worst case, your ellipse could be collapsed to just something lower dimensional, just a line or whatever the dimension of your space over here is. In which case little c would be 0 and then this would not be in force. And there is even a name for this condition on the right here, and it is the operator A is bounded from below. Okay, so we even squeezed a little definition in our lemma 8. Okay, in fact we are perfectly able to prove, well, at least this direction of lemma 8, and we are not quite able to prove that direction. We are missing one little ingredient, another Banach theorem. But yeah, let's keep this proof open. So if you wanna think about this, then we could do so in the forum, or you could ask me in the exercise sessions. Okay, so let's skip that proof. That's the good thing about being a professor. So if I ask you in the exam about a proof, then you shouldn't say no. But don't worry, I'm not going to ask you about that proof. Yeah. Or maybe one more comment on the proof still. For the direction that I said we are able to prove, you will need at some point completeness. So the word Hilbert in Hilbert space will actually come in, or in fact lemma 8 doesn't need scalar product, so you could do it in Banach space, but you need completeness. And by the way, you also need it for the other direction that we are not able to do. Okay, so this property, this boundedness from below, is not new to us. We saw this before. We saw it in the proof of Polsky's theorem. Well, maybe you can check back and agree quickly. And we're going to see it again today and probably in the future.